4, page 400. Given. The refrigerator has a weight, so the weight is 180 pounds of the refrigerator, so let's put an R. And it rests on a tile floor where mu is 0.25. Also the man, oh, they're going to give you two, so let's say refrigerator. Also the man has a weight, so the weight of the man is 150 pounds. And the coefficient of friction between the floor and his shoes, so I'm going to just say the mu of the man, is equal to 0.6. If he pushes horizontally on the refrigerator, determine if he can move it. If so, does the refrigerator slip or tip? So, when we talk about friction, it's just like any other statics problem. We're trying to prevent rotational motion, and we're trying to prevent translational motion. Translational motion can be called sliding in friction or slipping. Right? So this refrigerator, if I push it low enough, right, I could slide it. But if I push it too high, what am I going to do? I'm going to tip it. I'm going to cause a rotation. The two statics problems we did so far, the one block, what was happening to that one block on the incline we did on last week? It slid. What happened to these two blocks? Slid. What happened to this thing? It was in static equilibrium. It didn't do anything. But we were preventing it from rolling as well as sliding. Okay? So here we have a rectangular block. We have a refrigerator that could tip or slip. So let's draw the picture. We have this man pushing it, and it's at 4 feet. And here is where the center of gravity is of this thing, and it's 3 feet. And this right here is 3 feet. And right down here is the surface where it potentially could slide. So right now, what do they want us to know? They want to know if it's going to slip or slip or slide or tip. Don't hand it out yet. And does it ask us for a value? If he pushes horizontally on the refrigerator, determine if he can move it. So we don't know what the value is that he's going to push it at. So let's do our table. So force, moment, magnitude, direction. Let's just do the refrigerator to start. What is the refrigerator? This is the refridge. What is the refrigerator? What forces are on the refrigerator?
Normal weight.
Okay, the normal of the refrigerator. Do we know it? No? Direction? Sure. The weight of the refrigerator, did they give it to us? Yes, we know it.
Yeah.
What else is on there?
Friction.
The frictional force of the refrigerator, do we know it?
No.
No? Direction?
Yes.
Okay, anything else? The guy's pushing it, let's call it P. There's a P, do we know it? No, N? Do we know the direction? Yeah. So I only drew a table for the refrigerator. How many unknowns do we have?
3.
3 unknowns. How many equations do we need? 3 equations. How many bodies?
1.
1. What equations do we have? Sum of forces in the x, sum of forces in the y, the moment, and the friction equation. We have 4 equations. We only need 3. But we're analyzing for 2 different things, whether it slides or tips. When do you think you're going to use, which equation are you going to use for tipping? Moment equation. So let's analyze it for sliding first. Okay, so analyzing it for sliding, let's put all the forces in. So we have P in already, right? We have the normal. Do we call it normal sub? Yeah, from fridge. It's moving to the right, which way is the friction? Left. Friction for the refrigerator, and then we have the weight of the refrigerator, right? What is an unknown? This is an unknown, this is an unknown, this is an unknown. So what equation do you want to do first? So the force in the y. Some of the forces in the y equal nr minus wr equals 0. What does nr equal? Right, which is 180 pounds. What equation do you want to do next? Yes. Frictional is equal to mu, which is the refrigerator 0.25 times nr, which turns out to be, what's a quarter of 180? 45? Right, 45.90, yeah. What's the third equation you want to do? Some of the forces in the x. P minus the frictional force equals, and P is equal to 45 pounds. So in order for this to slide, what do you have to apply? A little more than 45. It's in static equilibrium right now. A little bit more than 45 pounds. Don't write all the numbers down, I have it. Kyle has it. A little bit more than 45 pounds is going to get this to slide. Okay, let's do the tipping part.
So we're not taking into account the weight of the man? Or
We're not worried about the man yet. We don't really care about him at all, except how much he's going to push. Why did they give you those extra information?
Oh.
2 reasons. 1, to confuse you, give you more information than you need. And 2, to set, like a real life problem. In a real life problem, you have a lot more information than you need to know. Okay? But we're analyzing the refrigerator. We decided we were going to analyze the refrigerator. We're analyzing the refrigerator. I don't care about the guy right now. Okay, so now let's analyze it for tipping. The only tricky part on this is when it starts to tip, what's it going to tip about?
The side,
Tell me where it is.
the right bottom corner.
Bottom corner, right? Bottom right corner. That's where it's going to tip, right? Because it's pushing it up here. So right now, while the refrigerator's down on the ground, the normal is in the center, right? It's always in the center of gravity. But if it starts to tip, where's the normal? It moves here. This is the tricky problem. This is the part that's tricky. Did you ever do a problem like this in physics? Okay, so now we have to redraw the problem. We still have P here, which is up 4 feet. We still have this being 3 feet. We still have this in the center, which is the weight of R. The only thing now is our normal is right here. So what equation, what's unknown? We have to redo the whole problem. So we still know that we have our frictional force right here, right? So we don't know P, we don't know the friction, we don't know N. So what equation do you want to do first? Some of the forces in Y. What happens? NR minus WR equals 0. The normal is the same. 180 pounds. What equation do you want to do next? This is 1.5, right? I always do some of the moments about the corner where it tips. Because you're going to get rid of N, right? Because this is up 3, this is only up, this is up 4, this is up 3. So I want to get rid of as many unknowns as I can. If I do it about this point, let's call it point 0, some of the moments about 0, what is it? WR times 1.5 negative, and then P times 4. What? Positive, thank you. P times 4 is negative, equals 0. And what does P turn out to be? Kyle, you have the sheet. What does P turn out to be?
P turns out to be 67.5 pounds.
67.5 pounds. And then we could go ahead, if we wanted, and use some of the forces in the X, but I'm gonna find the same thing, right?
How would you do that? So,
Some of the forces in the X, I got P minus frictional force. Ah, that's the same as the equation before. So what's different? What turned out to be different? What value turned out to be different between analyzing it for sliding and analyzing it for tipping? So, in order for it to slide, what do I have to apply? A little bit more than 45. In order to get it to tip, what do I have to do? Apply a little bit more than 67.5. If you go back to the problem says, if the man pushes horizontally, no, that's the wrong question. If he pushes horizontally on the refrigerator, determine if he can move it. Can the guy move it?
We didn't calculate his max push before he started sliding, right?
So we would have to analyze the guy, huh?
now we need
All right, well, we don't have time to analyze him, so let's just keep going. If the refrigerator does move, does it slip or tip first? Why? Because if you put only 45 pounds on it, it's going to slide first. Kyle, on that problem, did I analyze the guy as well?
Let's see. Yeah,
I did, okay. And what is
Wait.
P equal with him?
maybe you didn't. No, you didn't.
I didn't?
No.
Okay, so let's do the guy quickly. Okay, so we have this guy. He's pushing that way, P, so it's got to be, P's got to be this way. It's 4 feet up, right? It's not, the ground is level. Okay, then we have the weight.